Hey everyone. So welcome to this review lecture on vectorization and broadcasting. So till now in this series on deep learning, what we've covered is we've started with a neuron and got to a point where we know how to basically assemble a neural network from neurons, right? But a lot of what we saw was basically scalar operations. We did have a little bit of using Numpy, but we never really explored in detail what vectorization is. And so, what we do need to do when we start implementing, when we start vectorizing our neural networks, is to understand the basics. So, this is kind of a quick review to kind of get you up to speed with the concept of vectorization and broadcasting, right? In NumPy, which are very, very important concepts. Not necessarily if you're just implementing neural networks, but any computational problem using Python. This is something that is quite important to know. Okay, so let's get started. So let's take this expression, right? So let's say Z is W1x1 plus W2x2 plus W3x3 plus W4x4 plus W5x5. We are familiar with this, right? It's the summation part, without the bias term that we see in a neuron, right? The linear part of the neuron. Now, if you look at this, how many operations are there? So if you assume that this goes all the way to, this is 5, let's say in a general example for n terms, you have n multiplications, right? So this is 1 multiplication, 2, 3, 4, 5. So for n terms where n is 5, you'd have 5 multiplications. And then you have additions, right? So you'd have 4 additions, right? You'd have, this is 1 and then 2, 3, 4. So n multiplications and n minus 1 additions. Now, if you have, the reason I say n is this is 5, but you could have a system where, let's say you have the same thing, but now let's say you have 100 terms, right? So you have 100 multiplications and 99 additions. You could keep, increasing n. Now, how would you implement this, right, in Python? So you'd say sum is equal to 0 first, and then you'd say for I in range 0 to, in this case, 5, sum is equal to, or sum plus is equal to wi xi, assuming there's a w and an x. We'll see this, we'll implement this. So it's just an outline of what you'd see. Another way of implementing this is to say, what if we have a matrix, a column, a matrix W, right? It's a one-dimensional matrix. You can also set it up as a column matrix. You say 1, 5, minus 3, 2, 3. These are the values of W. So I'm just giving numbers. Let's say you have X and you have the same, five-dimensional matrix with 5 terms, basically 2, minus 3, minus 5, 2, and 7, right? So you have these W and X. Now, if you do a dot operation, right, W dot X, if you remember basic math, algebra, a dot operation is basically this, right? W1x1 plus W2x2 plus W3x3 and so on. So you'd effectively get exactly this, but right. And if you remember how we've implemented the neuron, for example, we have used the dot operation for this term, right? So you could do it in this fashion, or you could do this. Now, when you implement this dot, what you do is this is effectively implementing the dot product, right? But what you could do is say, well, I have numpy. I'm going to say z is numpy dot wx, right? So set up w, set up x. But then instead of doing it this way, you do this, right? So how different is that? Because the dot is effectively this operation, right? Well, let's just go check out some code and see what the difference is. When you kind of set it up like this, you use a loop in Python and kind of implement this, or you kind of fashion this as a couple of vectors and you do a numpy operation. So let's go take a look. Okay, so let's test out the dot product and see how vectorizing can create an improvement. So we import numpy as MP and we import time, right, which is a timing module. Okay, so what are we going to do? We're going to say, well, let's just find the number of inputs, right? And we're going to say that it's for now 1,000, right? And then we're going to say W is np dot random dot rand, right? Which is generating a random kind of vector that size, right? So the next is np dot random dot rand and inputs, right? It's an input, by the way. Yeah, okay. So let's run this. And if I print, say, W, you see what you get. So you get the idea, right? It's just a vector of that size. Or rather, in this case, it's numpy, so it's a matrix of that size. So it's a one-dimensional matrix. Okay. So now what we're going to do is let's try and create a sum, right? So we're going to say z, well, rather, let's do the dot product. So we're going to say z is 0.0, and we're going to say first start a loop. So we're going to say, we're going to start timing this. We're going to use a function called dot perf counter or performance counter, right? There's another way to do this, which is to use process time. The problem is, depending on the machine you use, sometimes process time might not work well enough. It might have an issue if you're using a Windows machine, for example. In some cases, or it might not work depending on the operating system. So performance counter, perf counter works well as far as I've seen. It's working well on different systems, right? So you can use that. So we say start is time.perf counter for I in range 0 to n inputs, right? And then what are we doing? We're saying z is z plus, which can be written as z plus equal to wi into x, right? So you've got the multiplication and the addition, and then we say end is time dot perf, which will again log the time, and then we want to check the time taken to. So we're going to say time is n minus start, right? And we're going to say this is time for looped, right? Okay. Now what about the unlooped? So this was just the dot product we printed. For the unlooped version, we're going to say, again, we can just copy this. So we can say start is perf counter, and then z is just np dot dot. So it's a lot simpler to use as well. It's end is time dot perf counter, and then we say print vectorized, and we say end, and let's just say start v and v, right? Start vectorized, end vectorized. We say n minus start, nv minus start. Okay. So let's run this. So it's a vector with 1,000 elements, right? What happens? Okay. So the loop, it's taking 0.0005 seconds. The unlooped, it's also taking, or the vectorized is also taking about the same, right? So not much of a difference. Okay, let's make this 10,000, right? Now rerun this. You see, it's 0.003. This is 0.007. Let's run it again. Okay, this is 0.003. This is 0.0001. Run it again. 0.005, 0.0003. So you already see that when you get to 10,000 elements, the dot product, it's already 10 times faster if you vectorize, right? This is 0.005. This is 0.0003. Now, depending on when you run on your system, depending on what the system is, if you're running background jobs, you'll see that the times are not always the same or consistent, but you'll start seeing this order of magnitude difference when you start getting to around 10,000, right? You can see it depending on your system. You can also see it earlier, but so even at 1,000, you might see a bit of difference. It's already faster vectorized, but they're about the same. You don't see that much of a difference, right? However, when you start getting to 10, as we've seen, there's a clear difference. When we get to 100,000, see, this is 0.03, this is 0.0003. So significantly faster, 100 times faster, right? So say by that, just by vectorizing your code, same operation, you are hitting, you're getting the operation done much, much faster, 100 times faster. What about when you're here? So a million, right? Again, this is again more than 100 times faster, right? 0.001 and this 0.3. So it's around 300 times faster, right? So you see how by vectorizing your code, 300 times faster means that something that would take you a day to run, if you don't vectorize it, it would take you a year to run, right? So that's significant. Now you'll say, where are you going to get a million sized matrix or a couple of vectors to do operations? One, if it's a matrix, you could have matrix dimensions that are smaller, but the elements would be high enough, right? The other point is you're looking at language models, for example, with billions of parameters, now trillions of parameters. So you are going to get these big, big matrices, when you vectorize your neural networks. So you really start seeing the difference here, right? What if we make this just a matrix multiplication? So what if we take out the plus and we just make it np dot, or rather we just say w into x, right, which is element-wise multiplication. Let's see what happens. So you say n inputs, random, and that, and that. Again, see, significant difference. Run it again, and run it again, run it a couple of. So when you want to check the timing, run it a few times so that the averages, you can take the averages. And again, you see that for 100,000 or a million in this case, points, W has a million elements basically. You see that this is taking 0.29 seconds and this is taking 0.003 seconds. So it's so much faster to vectorize it. Now you're saying 0.29 seconds doesn't sound bad. Well, if this was a neural network, right? Suppose you have more layers like this and you have to train on a billion data points, right? This is really going to make a difference, right? 0.29 times a billion is a really long time. Let's just put it that way. So getting that speed up here with vectorization is definitely the difference between something working and something not. So I've written element-wise matrix multiplication or vector multiplication. We've just done that right here. So let's just go back to the slides, and you'll see a plot there where I'm plotting how, depending on the number of operations you do, so which in this case number of inputs, you have the same number of operations. If it's just matrix multiplication, which is what we've done here, not the dot product, you can see how as you increase the number of inputs and so the number of operations, how like the time difference between a looped version in Python and a vectorized version is so much different. And the reason for that is here the loop is actually running in Python, whereas here you're calling a NumPy module. Both W and X are NumPy vectors, right, or matrices. And so effectively it's doing, NumPy is doing the multiplication, and NumPy uses pre-compiled C modules, right? So actually what you end up doing is you're running this code in C++, C or C++, which is much, much faster. And it's also optimized to take advantage of your CPU, and if you have a GPU of that and so on. So as a result of that, using NumPy is much faster. So what you should try and do then is, if you have a complex, large mathematical calculation, in this case, algebraic calculation, see if you can cast it into a matrix operation. And if you can, then using NumPy, right, makes things easier. Okay, so let's just go back to the slides for a bit. Okay, so we've seen how these two implementations differ, right? We see that in this case it's 5, so you see that it doesn't really matter. But when you start getting to a large number of operations, right, this is 500,000, then rather than using the loop, eliminating that and using NumPy operations significantly speeds up the computation, like we've seen. Right? So for the example we've seen, where we were just multiplying, the two vectors, the sum is not there, not the dot, just multiplying those two vectors. We see that, and this is on the log scale. So we've taken log of the number of operations. So 2 means it's 100, 3 is 1,000, 4 is 10,000, 100,000, and so on. And in this case, it's computational time again on the log scale. So -5 is actually 1e minus 5, right? -4 is 1e minus 4. -3 is 1e minus 3. -2 is 0.01. -1 is 0.1, and so on. Right? So it's on the log scale to show you how different this is. And you see that early on, it doesn't really make a difference. We've seen that when you get even smaller, so 5, 10, 100, they're very close. You won't see the difference. But when you start getting to a point where you have, a million operations, let's say, right? Now all of a sudden, this difference is very large. You're going from somewhere in the range of -3, -4, right? For large scale numbers to almost 0 or 1. So it's 3, 4 orders of magnitude. So 1,000 times faster sometimes. So how much of a difference is that? Well, it means that if your code would have taken 1 day to run and it was vectorized, right? And the red is vectorized and the blue is not vectorized. If your code was vectorized and it would take a day to run, if you didn't vectorize it, 1,000 times slower means it would take you 3 years to run, right? So you really start seeing the difference, right? It really makes a difference when you run big operations. And if you're thinking where these big operations come in deep learning, well, because obviously this is a course, the neurons we're implementing, the networks we're implementing are small in size. if you start building, GPT, right, for example, it's got millions, billions of parameters, right? Um, and now, in fact, the latest versions are in trillions of parameters. So the operations are exceptionally large. And so the difference between getting your model trained in time and just waiting forever is, in fact, vectorization is definitely a bottleneck. So just to kind of give you an outline, where can you use vectorization, right? So we've covered this operation, for example. You just forget the dot product. You're just saying W1 X1 is Z1, W2 X2 is Z2, W3 X3 is Z3, and so on. You see that each the operations are not dependent on each other, right? You have a W and an X. There's no dependence. So this Z1 does not come in anywhere here. There's no dependence. They're not dependent on each other, which means you can run them at the same time. You can compute them parallelly. So now when you make this, a couple of vectors or column matrices or whatever, and you use the numpy operation to get Z, in this case, it's just element-wise multiplication, which means this times this times this times this, and so on. You can just vectorize it. And because there's no dependence on each other, right, the vectorization works, right? On the other hand, if you take something like this, right, where there is a dependence, so you say Z0 is this, so you can say W0 in this case is 1. Say W1 Z1 is Z2, and then W2 Z2 is Z3, W3 Z3 is Z4, and so on. What do you get? Well, Z0 is fine, but in this case, right, to get Z2, which is required here, you need to first compute this. So you can't parallelize this because you don't know Z2, right? You can't use a NumPy matrix operation because you don't know Z2 till you compute this. And you don't know Z3 till you compute this. So in this case, doing a simple vectorization is not going to work, right? Because if you say W1, W2, W3 in one vector and Z1, Z2, Z3 in another vector, well, you don't know Z2 or Z3, right? And so vectorization is only possible, simple vectorization, if the operations are sequential, right? If they're not sequential, you're in trouble. Okay. So let's now go and kind of look at a few more examples. Now, the one question that does show up when you do vectorization is, why is this so much faster? So the answer is quite simple. When you kind of do the loops in Python, you're actually running proper Python, right? The loops are happening in Python. It's run the way, the interpreter runs the way normal Python does. And these commands, the way it's set up, it's a little slower. On the other hand, when you say you use a NumPy operation, NumPy is actually not running this loop in Python. It's technically still a loop, right? But it's not running a loop in Python. It's taking those vectors or matrices and passing it down to what are precompiled modules written in C, right? And so C or C++. And so what's happening is, under the hood, it's got these really optimized C or C++ modules optimized for vector operations. So they're compiled C or C++, which is much faster than Python to do a loop, right? It's much faster than Python. Two, it's optimized for matrix operations. So they're setting it up so that matrix operation can be done really well. They're also set up to take advantage of the architecture of the processors of CPUs as well. So things like hyperthreading, multi-threading, and of course, also of say GPUs. So if you have a GPU, you're running on a GPU, it's set up to take advantage of that as well. So combining all these factors, even without a GPU, it's still we're testing this on a CPU, right? It's still significantly faster because of this reason. So it's kind of depending on the precompiled linear algebra modules that it has. Okay, so now that we've got the basics, let's go do a few more implementations, and then we'll come back and explore the next topic. Right? Okay. Okay, so let's go now. Try this out for a few matrix operations. Right? Look at the impact of vectorizing. We're going to say number of elements in the matrix is 10. We're going to say A is np dot random dot rand. We're going to say n mat and mat and mat. So it's a 10 by 10 matrix. B is b dot random. And again, and mat and mat. And then we're going to have C, which is where the operations are going to be stored. We're going to say np dot zeros. And we're going to have it the same dimension. Mat let's set this up and let's just see what happens when you print A. Okay, it works. What if you print B? It's also okay. And you say C. Okay, good. So we want to first do addition. And so what are we going to do? We're going to say um, start is same thing. We can just copy this. Right? So we're going to say start is performance counter for I in range 0 to n mat, j in range 0 to n mat, right? C I j, right, is equal to A I j plus B. Actually, my bad. Yeah, J is A I j plus B I j, and that's it. We can just say n is time dot perf counter. And let's run this, right? And so say um, time print and say looped. Again, we've done that. And loop is n minus start. What happens when you vectorize it? Exceptionally simple. You just say that's numpy is the fun part. You say start v is time dot performance counter. Okay. You say c is a plus b. Now, yeah, okay. And we say and v is time dot performance counter. And we say print, and then the print of vectorized is nv minus start. So let's run the normal one. Take 0.000143, and the vectorized is 1e, in fact 9e minus 5. So it's definitely faster for a 10 by 10, so 100 operations. What if it's 100 by 100? So now you're at 10,000 operations, right? And you can really see how vectorization is so much faster, right? And if I make it 1,000 by 1,000, again, vectorization is so much faster, right? We're seeing a real difference, right? In this, it's 0.002 and it's 0.5, right? So almost 200 times upside by vectorizing addition. What if you're doing multiplication? This is element-wise multiplication. I'm just going to change the plus to multiply, and I'm going to change the plus here to multiply, right? Let's rerun this. So I'm going to actually, my mistake, I need to change this to multiplication. So rerun that and rerun this. Again, you see how much faster this is. Let's run this again. So then you see the order of magnitude difference is not changing, right? What I mean by that is this is 0.5 and this is 0.006, right? So that's the order of magnitude, as you'd say. And I can run it multiple times and average this, but we see that, it's still that much faster if it's a matrix operation. Now let's do something interesting, right? We've understood how vectorization works. We've seen now, so we are saying that actually we can cast our operations into matrix operations and use NumPy to run them, and it's much faster than writing our loops in Python, which means if you go back to a neural network, we can start taking out the loops that we've written and start figuring out how to cast those layers into matrix operations. Something to keep in mind, right? What if I have a matrix? So let's say I take the A from here and I say I have a scalar S, right? I say S is 3.0, right? Let's just print A. Right? So it's this big number. Now, if I say S times A, what happens? You see that the multiplication happens, right? Now, how does the multiplication happen, right? If you think about it, it shouldn't work, right? Because you're multiplying a scalar with your a matrix. How is this working? Now you can kind of think in your head how this works, and the obvious answer is NumPy is figuring out how to take the scalar and it's just multiplying each element. But how does NumPy do that? Let's look at another example, right? I'm going to do element-wise addition. So I'm going to say, let's just define another matrix. Let's say D is NP dot array. And I'm going to make it a two-dimensional matrix. I'm going to say 1, 2, 3, right? And then I'm going to say 4, 5, 6. Then let's say 7, 8, 9. Right? So D is a two-dimensional array. Now I'm going to say E is E dot array. What I'm going to do is make this effectively a column matrix. So how do you do that? It's basically got one column and multiple rows. So if I say E is now this. Now, can I add D and E? If you go by basic matrix algebra, it's not possible, right? Because D has three columns, three rows, and three columns, whereas E only has one column, right? It has three rows. And if I do D plus E, NumPy adds it for me. And what does it do? It says, well, it says 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is, yeah. And then it says 4 plus 2 is 6, 5 plus 2 is 7, 6 plus 2 is 8, and so on. So what it does is it basically puts this alongside this, and then it effectively is adding for this first column, it's adding each element by this, for this first row, it's adding each element here by this first row. For this second row, it's adding each element by the second row. And for this third row, it's adding each element by this third row. How does it know how to do that? Just like it knows how to do the scalar multiplication, right? It's using a process called broadcasting, right? And so let's just go back to the slides and understand how broadcasting works, because it's a really key concept. And once you understand broadcasting well, you already know vectorization, meaning we can make things, we can kind of formulate something as a matrix operation. You can use NumPy and it's much faster. But if you understand how broadcasting works, it makes it even easier to use NumPy, right? And its matrix operations to kind of solve our problems, especially with the context of neural networks. So let's just get back to the slides. Okay, so we obviously looked at the example of vectorization. What we also did then is look at how we could do an operation like this. So we did this exact operation where we took this matrix, right? And we tried and multiplied the scalar. Now, we're doing element-wise multiplication technically. How does NumPy kind of know what to do here, right? Because we're saying this is a matrix, this is, one value, it's a scalar. How does it know to multiply this properly, right? And so what NumPy does is an operation called broadcasting. What NumPy does is it follows a certain set of rules that we get to in detail. What it does is it takes the two matrices and then it kind of checks their compatibility. Now, in a scenario like this, so let's look at this particular example. It says, well, this is a scalar, this is a matrix. What I'm going to do is I'm going to stretch the scalar to match these dimensions. What do I mean by that? This is a 1 by 1 matrix effectively, right? A scalar is a 1 by 1 matrix. This is a 4 by 3 matrix. So it's just going to say, well, actually, I'm just going to extend this, stretch this. I'm going to add 4 rows and 3 columns, each containing the exact same number 2. Now what do you have? So we're doing element-wise multiplication. It's not matrix multiplication. Now what do we have? Now we have the same number of elements. We have 4 by 3. We have a 4 by 3 matrix here. Now you can multiply 1 with 2, 2 with 2, 3 with 2, 4 with 2, and so on, and get the answer. So what NumPy does is kind of stretch the scalar to match these dimensions. And this concept is called broadcasting. Let's look at another example. We've looked at this as well, right? What do you have here? You have a 4 by 1 matrix, so it's a column matrix effectively. You've got a 4 by 3, it's the same 4 by 3 matrix. So what do we see? NumPy says, well, this dimension is mismatched. This is 1 column, this is 3 columns. However, the next is matched. The next dimension, it's got 4 rows, it's got 4 rows. So it says, well, given you've given me this matrix and this matrix, what I'm going to do is, because the number of rows are the same, I'm going to try and match the columns, right? So how does it do that? Well, there's only one way to do that, right? You stretch it, which means you replicate or duplicate that row two more times, that column two more times. So now you end up with this. This is addition. Now what do you have? You have a 4 by 3 matrix and a 4 by 3 matrix. Addition is defined. So now you can go and add. You can do 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, and so on. Right? So this concept of stretching or extending a smaller matrix, if it's compatible based on certain rules, to match the larger matrix so that element-wise operations like addition or multiplication, element-wise addition or multiplication can be performed, is called broadcasting. So what happens in this example? So you have a 4 by 3 and a 3 by 1 matrix. Well, it says, okay, this is one column, maybe I can broadcast. But now what does it do? It says, well, this is 3 rows, this is 4 rows. So even if I stretch this, what happens here? This one dimension is not matching. Right? So Numpy will say, I'm sorry, I cannot broadcast this. So what you see is the one, if the one is there, it's fine, it considers it. But then if the other dimension does not match, right? In this case, the row dimension does not match, it's not going to broadcast. So you understand that in broadcasting, the dimensions to match, they either need to be a 1 and the other dimension is not 1, in which case it understands that I have to broadcast in the direction of 1, I have to stretch it in the direction of 1. But then all the other dimensions must match. Right? So this is another example, right? What happens here? Well, start from the right. We always start from the right. Well, this is 2 and this is 3. So how do you stretch this? Because if you stretch this, which, now I've used the same value 1, 2, 3, 4, 1, 2, 3, 4. Actually, I should use a different value 2, 3, 4, 5. How do I stretch this? I can I just take any one of them? I cannot, right? So it doesn't know how to stretch this. It says this is a compatible. Even though the number of rows is the same, it says I can't stretch this because the number of columns, if this was 1, or in this case, this column index was 1, it would say, okay, I'm going to stretch it. But because it's 2, it's going to say I cannot stretch it. So this operation is not defined. It cannot be. What about here? So, well, this is 1 by 3 operation, a matrix. This is a 4 by 3 matrix. So the column numbers match, 3 columns, 3 columns. Now it says, so that's compatible. It goes to the left, says, okay, this has got 4 rows, this has got 1 row. Now, because this is 1, I can match this by stretching it this way, right? So what can I do? I can say, well, I'm just going to duplicate this row 4 times. I'm going to say 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Now element-wise addition is defined. And I do the addition. I do 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 3 is 6, and so on. So let's take something now with one more dimension, so 3 dimensions. So you've got 2, 4, 3. The values will come up in a second. So it's 3-dimensional, and this is 2-dimensional. It's a 4 by 1 column matrix, right? Effectively. So first of all, how are we showing, this extra dimension? We're saying, well, the last dimension is the number of columns. The middle one is the number of rows. And then I'm showing the first dimension almost as an extra level or an extra layer, right? So this is like one layer and this is a second layer. That's how I'm indicating that third dimension, right? So it's technically a tensor, right? It's not a matrix, it's a tensor. It's got that third dimension. So first thing, I'm just going to write it out like this. Let's say this is dimension 1 and this is dimension 2, right? So 2, this is 1 and 2, and this is 4 by 1. So these are the rules that, or this is how Numpy tries to broadcast. First, it will say, okay, let's start from the rightmost dimension. And let's say, okay, this is 1. So this is the trailing dimension is the rightmost. So you say this is 1 and this is 3. If it's 1, either it should match. So if this was 3 and this is 3, it will say great. This is fine. In this case, this is 3 and this is 1. Because it's 1, it will say that's fine because I can still broadcast in that or stretch in that dimension. So it's compatible if the dimensions are equal or 1. So in this case, it's going to say 3 and 1, it's fine. I can stretch it in that direction. Goes to the next one. It says, okay, 4 and 4. They match. Very good. Now what? Well, there is no dimension here. There is a dimension here, right? So what do we do? Well, in the case of incompatible dimensions, this is 3-dimensional, this is 2-dimensional. It's going to add ones or pad to the left with as many ones as there are dimensions. So in this case, there's one more dimension. It's going to pad and say actually 1, 4, 1, right? It's going to make it a 1, 4, 1 matrix. And now it's going to check again. So we have left padded the dimension by 1. Now let's check again. So what do you do? Okay, so this needs to be stretched to 3. 4 and 4 is compatible. In this case, this is 2. Again, this is 1. We're lucky, right? So because this is 1, again, it can be broadcast. So first, let's broadcast this way. So let's take this 1, 2, 3, 4, 0, 1, 2, 3, 1, 2, 3, 4, and stretch it this way. So you end up with 3 and 3. So now this is compatible. There's still a missing dimension. 4 is fine. Number of rows is the same. So you don't need to worry about that. Because you don't need to worry about that, this is 1, 4, 3. We need to now stretch it, or rather add a layer, which is how we are defining the third dimension. So what does it do? It stretches it this way, adds the third dimension, as we say. And now that we've got this, it's compatible, right? It's 2, 4, 3, 2, 4, 3. We went from this, 1, 0, 2, 1 column, first stretching it this way to get this, matrix, then stretching it this way to get the full tensor. Now it's compatible and you can add, right? You can 1, 0, 1, you can say 1 plus 1 is 2, 0 plus 1 is 1, 1 plus 1 is 2, and so on. To check this out in Numpy, implement this, and you will see that this is the answer is, is if you sum this, what you will get with Numpy is the answer to that. So we've understood how Numpy takes this kind of vector or column matrix and broadcasts it in a way that allows us to handle matrices with more complex dimensions. This will come in very handy when we do, when we start vectorizing our neural net, right? So this is an example for you to try out, and then when the notes are up, I'll add this to the notes so you can check the answer there. We have a column matrix 1, 2, 3, so it's a 3 by 1 matrix, and we have this tensor, which is a 2, 1, 3, right? And so it's basically 2 rows, but now in tensor form 2, 0, 2, 1, 0, 1. Suppose we want to do an addition here or an element-wise multiplication. First question, can this be broadcast? And second question, if so, how is that going to work? What is the answer going to be? So do give it a shot. And when the notes are up, I can add the answer there. But what you can also do is, if you're watching this on YouTube, you can drop the comments. You can drop the answer in the comments, and I can post the answer in the comments. Okay. So hopefully you've understood this quite well. You've understood how this works. Vectorization and broadcasting is a key topic in Python, and we can now go and vectorize a neural network. So see you in the next.